Hello, my name is Alexander and you are on the DPLabs channel. Today we're going to make a second attempt at putting the scooter on the test stand. The first attempt was successful. I managed to burn out the motor in just 6 minutes at 26 kilowatts of power. It's not like I completely burned it out. There were a few issues that came up. The first issue was that I decided to experiment with the varnish for the windings. When heated, it reacted with the coolant, started to gradually peel off, and eventually blocked and clogged up the cooling system. The second issue, I installed the Hall sensor wires incorrectly, not taking into account the fact that the motor's gap is now extremely small, so the wire ended up rubbing against the magnets and eventually wore through over time. So I had to carefully disassemble the entire motor, thoroughly wash off all of the old varnish, soak it with fresh new varnish, plastic 71, replace the sensors, lay the wiring properly and neatly, reassemble everything, test it, and now it seems that everything is working fine. Besides the issues with the motor, a few other interesting things came up during the process, which I'll talk about in a bit more detail in just a moment. During testing, another nuance appeared. It turns out that it's not possible to load the motor at low RPMs on the test bench. This is an important limitation to note. Since we're dealing with a hub motor, its typical operating range is somewhere around 1,000, 1,500 RPM, at most around 2 to 200. That's 120 kilometers per hour with this tire diameter. The motor used as a load on the test bench is from a Leaf, and it's a high revving motor. And to increase the revolutions per minute, or RPM, on the output shaft, I added a reduction gear to the system, meaning I modified the gears that were already in place. Originally, we had 2 gears of exactly the same size, so there was no gear ratio between them at all. Now, on the hub motor, there is a large sprocket with 36 teeth, and here there is a smaller one with 12 teeth. This means the shaft will spin 3 times faster than before, and I will multiply all the sensor readings by 3 to account for this change. Why is the scooter lying on its side like this in the first place? I literally just installed the motor, tested it to make sure everything is working properly, and right now I'm carefully filling the cooling system with coolant. The intake port is located on the right side of the wheel, so in this position I can completely fill the motor. Yeah. Here we have the pump, and next to it there is a container that acts as an expansion tank. Now let's connect the pump. You can see bubbles moving through these hoses. We'll disconnect it now, flip it over, and I'll show you a bit more about how it spins without being connected to the test stand. All right, we've flipped it over. Now I'll spin the wheel, check that there are no leaks anywhere, and after that we'll take it to the test stand. Let's power up the controller. The controller is powered up. Turning it on. Here we can clearly see the idle consumption, that is 1 amp coming from the battery, 10 amps of phase current, and a battery voltage of 90.9 volts. Before approaching the motor, I'll put on safety glasses, because nothing pleases the eye quite like having a second eye. So what can I say? The chain really does sound quite terrible. Even though I spent all day yesterday just trying to tension it properly, I still couldn't really do anything about the constant, persistent noise. Yesterday, I experimented with the tensioner roller, tried placing it in several different spots, and adjusted the tension, but unfortunately, any position of the roller in the chain significantly increases power consumption. So I ended up tensioning the chain a different way. My goal was to achieve minimal power consumption so that this whole setup wouldn't waste extra energy. This is exactly the shaft that Dmitry mentioned in the first video about the scooter, the one Misha was supposed to hold if the test stand ran out.
He'll clamp the shaft with his hands and test it by feel. And
now I'll try to carefully hold on to it to see if I can actually stop it. Well, of course I'm not going to grab it with my bare hands, so instead I'll take a strip of sandpaper and try to stop it that way. I'm trying as hard as I possibly can, but you can clearly see the power consumption steadily increasing as I continue. It was 99 watts, now it's 145. The maximum I can load the shaft by hand is 45 watts of consumption. If you take into account that there's also 1 to 3 reduction here, then it's unrealistic. Looks like we've checked everything. We can take the scooter to the stand. Just ask for one more. Like this, I really think everything's good. Actually, I think it's awesome. I'm tidying up the wiring a bit, so it doesn't get caught in the chain. I'm making sure to be careful. I'm fastening the scooter securely to the frame with these kinds of sturdy bolts. There will be a total of 6 of them in place. So, what's the general principle of how the stand works? Our motor wheel is rigidly and securely fixed together with the shaft right here by the chain drive mechanism. This whole structure is firmly attached to the frame. Next, there's a sensor that straightforwardly and reliably transmits the torque to the shaft of the electric motor, which acts as the load. So everything is pulled together to one of the stages in order to carefully eliminate any unintended movement. All right, now I'm connecting the pump back right away and the controller as well. So what we have here is that we've connected just the leaf motor, specifically without any load attached, and now I want to check and observe the no load consumption. Right away I can see that the first readings have increased to 18 and the phase current has gone up by 5 amps. So it turns out that 163 watts and 63 to 64 watts are lost just to spin all of this equipment with absolutely no load at all. So what do we ultimately end up with? At idle, without any load, the torque fluctuates around 1 Newton meter and the power is between 65 and 73 watts. So that means we have 99 watts lost just to spin all this stuff, and that's the net power. Well, that's about right. Everything seems logical.
All right, let's give it a little twist. We're spinning it with our fingers. I don't know. I probably devoted about 17 years of my life to basketball, starting when I was 6, up until my late 20s or early 30s. I played in college for my school, took part in street ball tournaments, all sorts of things.
Finally, we've now reached the stage of actual testing at last. I'll try to explain the methodology. Right now, I want to gradually increase the RPM in 10% steps, starting from the minimum throttle setting. And at each RPM, apply a load and record absolutely all the data in a table. That means the load, the speed as a percentage, the battery current, the phase current, the RPM, the input power, the torque, and the output power at the shaft. I will have about 80 different measurements that will go into this chart, and then I will work with this information in detail, carefully analyzing the data. Let's start the motor at 10% of its maximum speed, and we'll gradually begin to apply the load. Now let's turn on the cruise control. By the way, just so you know, it might actually cut off if we add too much load. Okay, great. The power is now increased to a total of 600 watts and the torque at this particular moment is 5.5. Wait now. Go ahead. At this speed, our phase current has already increased to 310 amps, so we need to turn on the cooling system to prevent the motor from overheating. There it goes, that's 300 amps. It's rising, 310. Now it's going to reach its speed. The cruise control is working well. The wiring is shorter, thank you. Don't touch the wiring. Yeah, the sensor on the windings, in fact, actually increased in temperature to 70 degrees Celsius under 300 amps. Now it dropped. Yeah, it's already down to 9 degrees. Basically, the cooling system works well. Well, did you see how?
I just saw it.
So, what are the results of our hub motor testing? Let's take a closer look. This time, I didn't manage to burn anything, even though I really tried. The phase current reached a peak of about 450 to 480 amperes. The phase wires, of course, are smoking, but after a careful inspection, I didn't find any critical damage. The motor windings didn't heat up above 75 degrees. The sealing is intact, so I consider this a complete success. As for the torque, throughout almost the entire range, from about 10% up to 90% of the speed, the torque generally fluctuates between approximately 130 and 135 Newton meters. If you subtract the losses that come from the various transmissions, I believe the actual value would probably be a bit higher than that. But overall, I'm satisfied with the result.